The modern pinwheel calculator was invented in the 1870s in America by Frank Baldwin and in Europe by Vilgot Odhner. Pinwheel calculators were very popular in Europe, where tens of thousands were in use until the 1970s. Calculators based on Odhner's design were manufactured by many companies, including Brunsviga and Facet. The design shown in this video is a Triumphator Model K, manufactured in Germany around 1915. All pinwheel calculators featured metal wheels containing pins that extend radially and engage with a gear-driven accumulator register when the wheels are rotated. The number of pins that are extended can be set by rotating a slotted ring mounted to the pinwheel. Typically, 8 or more pinwheels in setting rings are assembled into a cylindrical rotor that is rotated by turning a handle. To perform an arithmetic operation, the user enters a number, for example 27, using the levers on the setting ring. Rotating the handle clockwise causes the number encoded by the setting rings to be added to the accumulator, while rotating counterclockwise results in subtracting the number from the accumulator. Each column of the accumulator register contains an intermediate gear, a numeral wheel, a detent lever, and a detent spring. As the pinwheel is turned, each extended pin engages the intermediate gear and advances the numeral wheel by 1 digit. The detent spring and the arms of the detent lever act as an escapement mechanism to prevent the numeral wheel from over-rotating. Carry operations are accomplished through the coordinated actions of the carry sensing lever and the carry finger. The carry sensing lever contains a small spring-loaded pin that presses against the side of the intermediate gear shaft, forcing the lever to be in either a forward or a rearward position. At the start of an addition, the carry sensing lever is set to its forward position. If the numeral wheel passes between 9 and 0 during an addition, a pointer on the numeral wheel pushes against the tip of the carry sensing lever and forces the lever into its rearward position. A ramped surface at the back of the lever is now positioned so as to deflect a spring-loaded carry finger on the next higher rotor disc, pushing the finger sideways into the path of the next higher intermediate gear, causing the gear to advance the next higher numeral wheel by 1 digit. After the carry operation is complete, a shoulder located near the back of the rotor disc pushes the carry sensing lever back into its forward position. When the carry sensing lever is in its forward position, the carry finger of the next higher rotor disc passes by uninterrupted and nothing happens. The location of the carry finger on each rotor disc is staggered to allow carry operations to ripple across the accumulator columns as needed. A second set of carry fingers is arranged symmetrically on the opposite side of the rotor to implement borrowing during subtraction operations. The Triumphator Model K supplements its 9 complete rotors with 4 partial rotors that only perform carry operations, allowing a wider operating range of numbers while reducing the cost of the calculator. The accumulator register is contained in a carriage that can be shifted to the left or right, allowing multiplication and division to be accomplished through a combination of repeated additions or subtractions and carriage shifts. The carriage movement is controlled by the shift lever, which fits into a set of slots in the base of the calculator that are aligned with the rotors. The carriage also contains a counting register that records the number of rotor turns during multiplication and division. The intermediate gears of the counter are driven by a single large tooth geared to the rotor shaft, which advances the current column by 1 digit each turn of the rotor. The design of the counter register differs from that of the accumulator in several ways. First, there is no carry mechanism, because it's never necessary to turn the rotor more than 9 times for any column. Second, the counter wheels are numbered in a special way to avoid displaying 9's complement values when the rotor is turned counterclockwise during subtraction. White numerals 0 through 8 are displayed for addition, and red numerals 1 through 9 are displayed for subtraction. The 0 and 9 are shared by both operations. Finally, because the numeral wheel has 18 teeth, the intermediate gear has only 9 teeth and is geared to the numeral wheel with a 2-to-1 reduction. The accumulator reset mechanism works as follows. The center part of each numeral wheel is hollow, except for a small tab on the right side of the wheel, located between the 9 and 0 digits. The accumulator shaft contains metal teeth that are normally located on the left side of the hollow wheel, allowing the wheels to turn freely. When the accumulator reset lever is twisted, a cam on the face of the shaft bushing pushes the shaft outward slightly, causing the teeth to move to the right side of the numeral wheels, where they will engage the tabs and turn the wheels towards 0. After a full revolution, the shaft returns to its original location and the keys disengage the tabs. A similar mechanism is used to clear the counting register. When it's not turning, the rotor can be locked in a resting position by inserting a spring-loaded pin inside the handle into a matching hole in the lower handle bushing. Locking the rotor causes 3 safety interlock mechanisms to disengage. The first interlock prevents users from changing the setting rings while the rotor is turning. This is implemented by a rotor locking bar, which has a series of notches that can allow or block movement of the setting rings. A spring pressing against the locking bar keeps it in blocking position while the rotor is turning. When the rotor is locked in its rest position, the handle's locking pin pushes against a rod attached to an arm that presses the locking bar into the open position, allowing the setting rings to rotate. The second interlock prevents users from shifting the carriage while the rotor is turning. This interlock consists of a slotted disc and an arm that is lifted by the carriage shift lever while the shift is in progress. The arm has a protrusion that must be aligned with the slot in the disc in order to allow the carriage shift lever to be depressed. The arm is aligned with the disc only when the rotor is locked. The third interlock prevents users from clearing the registers while the rotor is turning. The third interlock actually utilizes the mechanisms of the second interlock. 2 arms extend from the back of the carriage shift lever and fit into a depression on the faces of the center bushings of the registers. When a register reset lever is twisted, the bushing turns and pushes on the arms, forcing the carriage shift lever downward. If the rotor is turning, the carriage shift lever is locked in the up position, which prevents the arms from moving, which prevents the bushing from turning, and which prevents the reset lever from twisting.